I'm with you. It's if you ask me to talk about, you know, multivariate calculus, I don't know. I took the class, I think I got a B in it, but I don't remember any of it. It a little bit of it shows up here and there again. As it shows itself up, you'll see. Let's just get your feet back in the algebra. I do. Solving systems of equations is basically what we're working through today. And I know I really don't want to talk over everybody, okay? There's a lot of you, and we don't have that much time to get through the material. When you're working with systems of equations, Miss Fleming.
On your website, going to the homework unit thing, shouldn't we be doing 3-1?
I'm skipping it. Didn't I put a little asterisk in there, subject to change? I should. I gotta change that. I'll make myself a note to change that because it's there was a lot of other things on there that bless you, didn't really need to do. So when we're solving systems of equations, there are multiple methods to solve systems of equations. We have substitution.
Bless you.
Elimination.
Oh, we did these last year too.
Elimination. Is it 9?
Yeah.
It is today. And then linear combinations. Each one of these three methods has its own merit, and there are certain scenarios that one way is easier to use than others, and there are certain scenarios where one way is more difficult than others. A lot of times it works out to become preference as far as how you want to solve. In this unit, and this is kind of where it starts out, in 3.1 it's graphing systems. That's a waste of time. There's no reason to graph systems. It's so much easier to use algebra to get to the result right off the bat. So that's why I'm like halfway through writing all those lessons, like, why am I doing this? This is stupid. So I'm not going to do it. So when I'm looking at substitution is when you're putting something in for something else. The easiest way to do that is if you already have a variable solved by itself. So if you already have something that says y equals 3x, and then the next equation, I just substitute in for y. 3x. When I'm doing elimination, that's when it's easy for me to eliminate one of my variables. If I happen to have the same coefficient with the same sign, I'd subtract the two together. Same coefficient, different signs, I'd add them together to eliminate one of my variables. And then the last one is this linear combinations. It's when you're multiplying it by a specific factor to create create an elimination style problem. And that's the style that you guys are probably most accustomed to doing because it's sometimes can tend to be a little bit more of the complex one, but without being too overly complex. For example, if I start with looking at this first one here, 3x, 4y is -4, x plus 2y is 2. There are two methods that are shining right off the bat that I'm looking at doing here. I could do a substitution rather quickly by moving the 2y over. Do you agree?
Sure.
Or I can do a linear combination just by multiplying the second equation by 2 and subtracting. And that's how my mind works too. Okay? She was saying that that's the way that she would have set it up, is just multiply the bottom equation by 2 to be able to subtract 4s. Okay? There's more than one way to set up problems. And then you re-substitute back in. So let's do, what do you want to do, substitution or elimination here? We'll do them both. If I do substitution, I'm going to say x equals 2 minus 2y. Everybody okay with that?
Sure.
I take this value of x and I substitute back in. 3 times the quantity, 2 minus 2y, plus a 4y is a -4. And now I'm at a multi-step equation. Distribute and solve. We have a 6 minus a 6y plus a 4y is a negative 4. Combine my like terms, move the 6, I get negative 2y is negative 10. Y is 5.
Can you scroll up a little bit so I can see that?
Yeah.
And now we remember this.
That's how I solve the equation to get y. Yeah. And then I just substitute that back in to get x. So then I take this back to here. 2 minus 2 times 5 is negative 8. And when we're looking at these linear combinations, where I'm looking to solve the system of equations, I'm looking at basically where two lines intersect, which means my answers are always going to be ordered pairs. So my ordered pair here would be negative 8, comma 5.
What?
And that's how I set them up.
I thought it was plus 2y, not minus 2y.
I got x by itself right away.
Yeah, but then when you substitute the y back in, it would be plus 10, not minus 10.
Well, then I'd have x plus 10 is 2. X is still negative 8. Okay. What I was doing there is, since I already had x by itself, might as well just reuse that equation. That was one way. If I went the other way and I used the linear combination method, I'd be looking at doing one of two things. Now I'll put them up on a split screen so you guys can see the why you would choose one way versus the other. If I look at this the other way of doing things, I can pick a variable to eliminate via subtraction. Does it matter which one I pick, whether it's y or x? No. I see things and I see things that are even right away, so I'd say, hey, I'm going to do this. I want to multiply this second equation by 2. When I do that, I get 3x, 4y, negative 4, 2x, 4y, and a 4. Now I have same coefficients, same signs, excuse me. How could I eliminate 4y? So what would I have to do to the two equations? Subtraction. So I'd split this into 3 subtraction problems. Yeah, but sometimes you're not going to do substitutions.
This one makes so much more sense.
That's fine. And that's why it's depends on how you see it. You can always do linear combinations. It'll always work. What's 3 minus 2? 4 minus 4 is gone. What's negative 4 minus 4? X is negative 8. Go back up. You have negative 8 plus 2y is 2. Add 8. Divide by 2. Totally up to you how you want to set it up, guys. Either method works. Either method's going to work. It's just a matter of getting accustomed to how you want to set it up. Okay? It's just a matter of that.
Wait, is this all we're doing?
Yeah.
That was a linear combination.
So, wait. What are
Geometry the one that you just did. It was easy in the beginning, and we thought it was so easy that we asked our first test and realized maybe not so easy.
Yes. Okay, so
We're just starting.
if you would do
What's that?
minus 2y, and this would be 2.
How'd I do that first one?
Actually, 2 minus 2y.
I can't hear you. Everybody else is talking. Shh, guys. That first one, the first time I did that, Lori, we used substitution. Since x was almost already by itself, we just moved stuff around. Show you another one.
Wait,
Mr. Murphy,
Yeah.
the one you just did, which was that?
Combination, linear combination.
to get that. There's one for one.
That was a linear combination, so I had to multiply it out. Linear combination turns into elimination after one step.
so now you're doing
Again, Same idea. I have 3x minus y is 13. 2x plus 2y is negative 10. Right off the bat, neither one of those equations has the same coefficient with the same sign, the same coefficient with opposite signs. So I cannot just use elimination right away. There are multiple different ways to set this one up. One way that I see right away is that I can either multiply the top equation by 2, or what can I do with the second equation? Cut it in half. Very good. Everybody see why I can multiply that one, the second one, I can cut it in half? Because they're all even, and that would eliminate the y values right away. I think I would do that method. And again, this is another linear combination because I can multiply everything here by a half. And I would get 3x minus y is 13. What's half of 2? What's half of 2? And what's half of negative 10?
5.
Good. So what do I do to eliminate the y values then? I add them together. So this is where it comes in, like I was saying, I'm doing linear combination first, and then all of a sudden it turns into an elimination problem because I can just add them together and I have eliminated the y values. But I had to come up with some scalar multiplier to be able to do that first. So even though I say there's these 3 methods, no matter what, if you're doing linear combination, you're eventually going to have to eliminate something. Okay? So it's not always going to be evident which method to choose. Sometimes you have to mess with the numbers. Sometimes it is blatantly obvious what you're going to do. Okay? So if you started with this problem to begin with, you'd say, oh, just going to eliminate, add the y's together, done. So if I split this up and I add everything, what's 3 plus 1?
4.
13 and a negative 5?
8.
X is?
2.
Very good. 2 plus what is negative 5?
Negative 7.
Very good. And that's where those 2 lines intersect. If you want to get really rambunctious with this stuff to double check all of your work, could you go to your y equals and get both equations by in the slope-intercept form, find the intersection of the lines. It'll show you the answers. Sir?
Wait, so for elimination, we add the 2.
Or subtract the 2, depending on the scenario.
Okay.
Remember, elimination can be one of 2 methods. You can either, if you have the same sign, same coefficient, subtract. Same sign, same coefficient, different signs, like x and a negative x, you add them together and they go away.
Okay.
All right? That's okay, it's all right. And like I said, it's just, this is one of those sections that you'll see it and go, oh, dang it, I forgot how to add.
There's different ways to solve. So it's like whatever one.
Yeah, whichever one fits, and that's the idea. What happens if you get something, if you go through all of your elimination stuff and you get something like this? Let's say you go through and you set everything up and all of a sudden your equation says 4 equals 4.
Then you got it right?
So what's your answer then? Yeah. You could have, but what happens if you get something like this and you did everything right and everything looks like it's all good?
It's just a line.
Do 0 equals
No. What's the opposite of no solution?
All
All real numbers. But if you get to something like this where it says, and you didn't goof, this would be your no solution.
That'd be the circle.
This is the circle of death. It happens from time to time where what happens is you get you wind up with the exact same equation. An all real number problem would look like this.
Wait, no.
Yeah, that'd be great.
Oh yeah, that would work, wouldn't it?
Because X would be 1 and Y would be 1.
Yes. Good. Well, wait, no, this isn't one. I'm trying to think of one that works. I don't think that's right. Anyway, if you wind up with the same thing on both sides of the equal sign and you didn't done goof, that means that it's all real numbers. If you get different things on both sides of the equal sign and you didn't done goof, it's no answer, no solution, excuse me. I think I did have an example here.
I'll just take your word.
Ah, it's this one. Let's try this one. We got a couple minutes. Negative x plus y is negative 2. And 2x minus 2y is 0. Again, this winds up being one of the types of problems that you just pick what you want to work with. Do you want to? You're obviously going to have to do some sort of linear combination to get the same coefficients. Do you want to multiply the top equation, or do you want to cut the bottom equation in half? Does it matter? No. What do you want to do? Multiply the top. What do you multiply the top by? 2. If I multiply the top equation by 2, I'm just going to write it directly below the one that's already here. I'm going to get negative 2x plus 2y is negative 4. You okay with that? So now, same coefficients, same sides. Uh-oh. If I add these together, 0 plus 0 equals negative 4. Does 0 equal negative 4?
No.
So my answer would be no solution. Does that make sense?
No.
That just means they have the same slope. That's all it means. They have the same slope, they're parallel lines. They're never going to intersect each other. That's all. If there's all real solutions or all real numbers, it just means it might be in the exact same line. That's why they have infinite solutions. Intersect, that's fine.
So like the solution of it is like what you're kind of looking for is like where graph
And graphing, there's nothing wrong with doing the graphing part. It's just so inefficient. That's why I just don't try to graph. Okay. Let me give you guys, I think I have, 7 problems, I think? It is it's in the book, it's on page 147, 44,
44, 49, and problem 54.
and problem 54, very good. I already posted that on the calendar, so it's on the website on the calendar as well. I do know that you can get to the book still. Eventually, I'll put these things in that Math Excel thing, and then the assignments will post through. It'll be a little bit cleaner. But, like I said, we shall see how many of those emails I get throughout the evening tonight. Not frustrating. So, okay. Is anybody's Chromebook not getting to the actual textbook okay? Is everybody getting there? Sometimes, or is it you're all right?
No, sometimes it doesn't. Sometimes it does.
Does anybody who has an Android phone? Have you been able to access the textbook on an Android phone? Would you try and let me know if it works or not? I know I watched somebody try to get on the website with with an iPhone and go to the Pearson book, and Pearson won't let you use an iPhone on their website, which I think is just absolutely stupid. I don't know why. It makes no sense to me. It would make the most sense that if somebody wants to do their homework and they have access codes to get into this website, you should be able to use whatever means necessary to use the website. I don't know, call me crazy for thinking logically here.
You're crazy.
Crazy!
You know what's making me crazy?
You're
I'm not only